should now return to your normal seats.
Food,
Waiting.
get your hands off my pocket.
I'm starting to record now. I need everybody to be quiet. Thank you. All right, so we're going to go ahead and get started. Let's just run through the bell words real quick. Most people did well with the first 2 marks. Name J, it's 2-iodo, 2-methyl butane. 1 mark for that. I will say that at the end of the year in the past, about half the students get this wrong. Where do you think that it goes wrong, Alina? The alphabetical order. A lot of times students will put the methyl first and not the iodo, and then you don't get the mark, unfortunately. So make sure that you alphabetize from organic part 1 your substituents. It's literally just check it alphabetically. Next one, fully name the mechanism. You do not have to specify whether it's SN1 or SN2 when you fully name, but you do have to say that it's a nucleophilic substitution. And so that's what it is. And then finally, the mechanism. A lot of people were choosing the wrong mechanism at first. You got to be careful here. This would be, and I'm just going to use how they present it to me. This is a SN1. It's SN1, meaning that the leaving group leaves first. And that's the key difference. The leaving group leaves first before the other group can come in. Yes?
Why?
Because the NA is a spectator. However, we can include the NA, and I'll show you how. So the first thing that happens though is this. You've got a partial positive carbon, and you've got the partial negative iodine, and the 2 electrons go with the iodine. And so you end up with this, with a carbocation right there, right? Then technically, if you write everything, which you do not have to do, but if you wrote everything, you would write that you have the I- there, right? You have Na+ there in water, don't you? And you have OH-. You have, this is aqueous, but that means it's dissolved in water, right? You've got both of these in water, dissolved and separated from each other. So far, so good? Out of three things that are available in the water, only one of them is going to get into that molecule. Which one is it? And that's why writing more actually can confuse you. Because you're like, well, which one would do it? It's going to be the best nucleophile, which is the OH, is what reacts, right? And adds in. And so your answer here would be OH. And what would your byproduct be? It's technically, if you wanted it to be completely balanced, it would be NaI. AQ, right? Do you have to include the byproduct?
No.
Typically, no. If it makes you feel better to show that everything's there, you can. But if it confuses you to show everything's there, then you only have to show the OH-. Whichever one's less confusing for you is the way I would go. All right, good? So that was what we did last class. We did SN1 mechanisms, which is what that was for tertiary halogen alkanes, and we did SN2 mechanisms for primary halogen alkanes. Today, we are going over the second part of redox. So it is going to be partially some things you know already. I'm also going to do a quick review to help you organize your thoughts. That's where it says starburst for alkenes. We're going to organize our thoughts with how alkenes are. We'll do that after the lesson though, to make sure we have enough time to do that and then for you to practice. We have, that's a lot of objectives. We have a lot of objectives, but some of them you may be quite familiar with already. So put a check mark on those things you already know. I just copy pasted down from the syllabus. So it says under alcohol, recall the reactions, both the reagents, which is a synonym for reactants, and conditions by which alcohols can be produced. Did you know if you added H2O gas to an alkene, you would get an alcohol? Did you know that? we already learned this? You should say yes. This is in your flashcards, isn't it? We did this already. Reaction of alkenes with cold, dilute, acid, KMNO4 to form a diol. Have we done that?
Yes.
Let's take a look at that. I'm using skeletal just for space. So we've got this plus KMNO4, H plus, and cold, right? And what would the result of this example be? OH and OH. And OH to each side of the alkene, specifically. We've done that already. Substitution of a halogen alkane. Wasn't that literally the Bellward question? Isn't that what we did in the Bellward? We've already done this. I'm just putting check marks that we already did that. It looks like it's a lot, but some of this we've already done. Reduction of an aldehyde, that we haven't done yet. We've only done some oxidations, but we have not done reduction. So this is going to be today. I'm going to put an X here because we haven't done it yet. And E, reduction of carboxylic acid, we haven't done that yet. All right, the next one says, classify alcohols as primary, secondary, tertiary. Do you know how to do that already? And by the way, there's a lot of times you get repeat objectives. They'll say, classify this as primary, secondary, tertiary. Classify that as primary, secondary, tertiary. Well, we've done that. So put a check marks. And then B, put an X on because this is something we're going to learn today. That's why I included this objective in here. State characteristic, distinguishing reactions, and the color change. This is a chemical test that you will want to write a flashcard on and that we're going to do a lab on in a few weeks. Not next week, but the week after. Aldehydes and ketones. We're going to look at oxidizing, and this is where I said last class, if you were here last class, some of you were bringing up K2CR207, and I had put it in the homework, but I told you you didn't have to. Look what it says here. You can oxidize alcohols using either K2CR207 or KMNO4. So you can use either of these two. As long as they've got lots of oxygen, that's what you're looking for to oxidize. Lots of oxygen. So K2CR207 and KMNO4 are excellent examples of this. If I didn't include the spectators, how would I have written them? You could also write this as CR207, 2 minus. And this is how it's sometimes written in some questions. Don't let this throw you off. They're just not including the metal spectator ion. Or MnO4 minus. And if they said words, what would they say? Like they could also say words. What is CR207? So this is dichromate, right? Polyatomic ion. And this is permanganate. These were a couple of the polyatomic ions I told you to memorize earlier in the year, specifically because they show up here. And you need to know them by name, that they show up. And then this is the last one. Oxidation of secondary alcohols and distillation to produce ketones. So it looks like a lot more than it is. Look at all the stuff that I check marked, the stuff I have X's, and the stuff I haven't yet taught you. So half of these we've already done, and half of these are new to us today. So last time we did redox, and I haven't given you a mini assessment on redox yet. That's happening today. The KMNO4 hot and cold. I hope you studied those because that's going to be on today's, right? But you're also going to see it here. Oxidation and reduction. There's some things you need to memorize, but there's some strategies I can give you to help. Primary alcohols always oxidize to become aldehydes, which, unless you do something special, further oxidize to automatically become carboxylic acid. We actually kind of already covered this. I told you if that when you did a hot KMNO4 reaction, you had an aldehyde, it would automatically become a carboxylic acid. You would add an extra O to it. Secondary alcohols always become ketones, and tertiary alcohols cannot be oxidized. What does that mean? You're going to have to tell really quickly. You're going to have to know if you have a primary, secondary, or tertiary alcohol. And we're going to take a look at how each of these results happen. And so this would be the alcohol you start with, right? Starting organic reactant. K2CR207, they said or something else. What was the or something else they could give you instead? Or KMNO4. And instead of saying dilute H2SO4, what could we instead write? H plus, right? We could just write H plus for acid. Instead of naming it, we can write H plus because it's just strong acid. All right, so we're going to go through the process of how this happens, and you want to pay careful attention to the process because if you can remember it this way, then you don't have to do like 10 different flashcards or 6 different flashcards because this is going to help you to remember what to do. So let's take a look at primary alcohol, and I wrote it in here, so I'm going to write it on the side. How does this tell me I have a primary alcohol? Oh, this is secondary. How do I know I have a primary alcohol?
That's only bonded to one C, which is the R.
R stands for carbon groups, or the rest of the chain, rest of the carbon chain. And so if I see a carbon next to one R group, this tells me that it's primary. So pay attention real carefully to this process. First thing you got to remember is oxidation either means one of two things. You remember what those two things are for organic chemists and biologists? Oxidation means what?
Addition of oxygen.
Right. Take away hydrogen and or, right? Add oxygen. Either one or both of those things happen for you to have oxidation. So, watch this. Take the hydrogen away from the oxygen. I'm going to do it in a different color. Take a hydrogen away from the carbon next door. Right here. Or the one on the top, doesn't matter. What would happen if you took those two hydrogens away? You would get, just holding on the same stuff, CRHO, but right now we don't satisfy the octet rule. So you would need to put a double bond. The same way when we took away two atoms, we formed a double bond between two carbons. The same thing you should see is happening here. We're taking away two atoms of hydrogen and forming a double bond. Well, what functional group is this? So a primary alcohol will always turn into an aldehyde. But one of the things we learned about it was about a week and a half ago, so I don't blame you if you forgot. If you end up with this C double bond O and an H right there, you're supposed to add something immediately to it. An oxygen to any hydrogen. And so this would turn into a carboxylic acid, which is what's being described to you right here. So in this process, you're taking away two hydrogens. And what are you doing here? Adding one
Adding a double bond.
oxygen. You put the double bond here, right? This is the double bond. So you took away two hydrogens and made a double bond, and then you added an oxygen, and that gives you a carboxylic acid. Typically, this all happens at once, meaning when you make the aldehyde, not far long after the oxygen gets added in, it further oxidizes to a carboxylic acid. You're going to learn today in the lesson, it's one of the last things we talk about, that in order to keep an aldehyde as an aldehyde, you have to do something special to it. You can write the word down because it's a key word. It's called distill. If you want to keep an aldehyde and not turn it to a carboxylic acid, you have to distill the aldehyde off, which I'm going to explain what that is. You'll see it in a future slide, but just so you have an idea. Otherwise, it just goes straight to carboxylic acid. All right, what happens if you have a secondary alcohol? Let's pay careful attention to that one. Take away the two hydrogens. What happens? Here, from secondary alcohol. What happens when you take away the two hydrogens? Like you can trace along.
So then the double bond O.
You get a double bond O, which automatically turns it into a ketone. Ketones cannot be further oxidized. You may want to write that here because there's no hydrogen to add the oxygen to. So ketones cannot be further oxidized. Ketones stay ketones. Ketones stay ketones. You cannot oxidize them any further because there's no hydrogen to add oxygen to.
And tertiary alcohols stay alcohols.
Right. And so let's explain why. Tertiary alcohol. You have to take away two hydrogens the first step, right? So take away two hydrogens. Where's the hydrogen at on this carbon to make the double bond? It has to be on this one because you got to make the double bond between two, right? So is there hydrogen there? No reaction. Tertiary alcohols stay alcohol.
So just put no reaction.
Yeah. So guess what? There's going to be options for no reactions coming up on future quizzes. H plus and heat. H plus and heat. So if you want to add and heat under reflux, specifically, to fill in the rest of the position. What? That's your starting organic reaction. So you always start with that. So let's say that you had this. What would your product be? So this is how you write it if you want your example reaction. What would your product be? Because you get this, right? Gotta take that hydrogen away. You can't leave that as a single bond. You have to turn that into a and then there. This is the ketone. Ketone stay. Ketone. Stay. Only aldehydes change to carboxylic acid. Ketone stay. One more, just to look at. What if you had this plus K2Cr2O7H plus heat under reflux? You should at least say heat. Sometimes they specify under reflux is needed. Reflux means you're boiling it. So I would include it. Yes. Yeah. What's this? How many carbons and what type of functional group?
Carboxylic acid.
How many carbons? 1, 2, 3. It's on carbon 1, but it's a carboxylic acid, right? Just to give you a couple examples. Carboxylic acid is the most oxidized form of a functional group you can have because it has the most amount of oxygen in it. And alcohol is the most reduced. And so what you're going to see when you go back to, I'm going to go back to that other slide we were on. What you're going to see is you saw the letter O in brackets, and then you see the letter H in brackets going the opposite direction. What do you think that means? Oxidation is this way. Reduction is that way. And so it's the same reactions, but they're inverse of each other. So you can't reduce alcohols anymore, but you can reduce carboxylic acid. And you would do the opposite thing. From a carboxylic acid to an aldehyde, you would take away an oxygen. And from an aldehyde to an alcohol, you would add 2 hydrogens. And so you'll see that later in today's lesson. Let's take a look at a Cambridge question. This was one that I used to put in the lesson on alkenes, but I figured it's better to do here now that we've learned what to do with alcohol. And they're hitting you with some fun facts. The compound Hex 3-ene-1-all P has a strong leafy smell. Smells like a newly cut grass, which they use for perfume. So if you want to smell like grass in your perfume, you can use Hex 3-ene-1-all. Hitting with those fun facts. I don't know why you would want to smell like a leaf, but okay. What is produced when P is treated with an excess of hot concentrated KMNO4? Do you remember what to do?
You gotta break the middle one and add a whole.
So we know we're going to get CH3, CH2, C, double bond O, and H, right? So this is what you get from the left side, do you agree? And then the right side, just cutting it, would be double bond OCH again, and then CH2, CH2OH. This was the first step. I gave you a process. I told you the first thing we do is we split it into two, and we add oxygens on each side.
Yeah.
If we see there's a hydrogen on the carbon right next door, we add in.
Oxygen.
So we know that this actually has to be a carboxylic acid, and this also has to be a. Now, what did we just learn? Is there anything else that can be oxidized here besides the alkene?
The alcohol.
The alcohol will also be oxidized.
And
So how would that happen?
we would still split it the same way if it was cold concentrated acid.
If it was cold, your answer would have been CH3, CH2, CHOH, CHOH, CH2, CH2OH.
Oh, so double bond O.
Right?
Oh, yeah, that single bond O.
If it was cold,
Oh.
you would break just the double bond, not the single bond. It would be one product, and you would add the OHs to each side, right? But this is asking hot, which means you break both bonds. You get the carboxylic acid on both sides, and because it is hot, what do we do to the OH? This also has to be oxidized, right? What type of alcohol is this? Which means it's turning into yet another on the second carbon here. CH2 and then COOH from here to here. So which answer is that? Like, it's multiple choice. You didn't have to draw it all out. The answer is definitely, you could have taken A and B out immediately because you needed to have two products. So that gets you between C and D. This one says it stays at an aldehyde, and that's not true. So the answer has to be D. Good? Oh, wow. If you don't know your functional groups, this is going to get rough right now. Because what we're doing is functional group transformations, right? So you've got to know what functional group you have. It's an easy way to be able to come up with your answers. They are. No? Not fun? All right. So the next slide when you're ready is chemical tests. This is a chemical test we're going to do in a couple of weeks, like I said. It's called the potassium dichromate test. And it turns out, I was going to see, but I had my lab aids took some of the chemicals away, so I'm not exactly sure where it is. Potassium dichromate is a bright orange. I think I'll pull it up. Over here. Potassium dichromate. It is a bright orange. You may recognize it if you were here for Spooky Science, as I used it for something called the Hellfire reaction. It looks like a orange and then it burns black with an orange ring around it when we set it on fire. Fun stuff. But this is potassium dichromate. What color is that? It's actually orange, believe it or not. It is like a dark, deep orange. What do you think is giving it its color? The chromium. Transition metals have deep colors. So the color is actually coming from the chromium. This is fun facts, but it helps aid you with knowing, oh, that's why the color changes. It's because it has a transition metal in it. The transition metals are what have color changes. And so this is the reaction to show for if this reaction actually happens or not. What we do is we add potassium dichromate to all of our sample alcohols. If you have a primary or secondary alcohol, the solution will turn from orange to green. And green means that your alcohol was oxidized. So we use the change in color of chromium as it goes through its different transition states, its oxidation states, to show that the alcohol has been oxidized. And this will happen if we have a primary alcohol. It'll happen if we have a secondary alcohol. What other groups would show oxidation with potassium dichromate? Primary alcohol, secondary alcohol, what other groups would show a positive test? That if I put potassium chromate and I warmed it in a test tube, that it would change from orange to green. We know the primary alcohols react, we know the secondary alcohols react, what else reacts? Aldehyde. So this also would be a test for aldehyde. And what would stay orange? So if oxidized turns green, if no reaction, stays yellow. Ketone would stay yellow. Carboxylic acid would stay yellow because it's already oxidized, right? So carboxylic acid would stay yellow. What else? There's something else. What else would stay yellow if I added potassium dichromate to it? Tertiary alcohol, right? So anything that doesn't react will stay yellow, meaning the potassium dichromate stays dichromate. Interesting point of note that it says here in the book, if you have the book, by the way, if you're renting the book from me, this diagram is from the book. And it tells you that dichromate is changing from Cr2O7 minus in this process to Cr3 plus. What do you think is happening to the chromium? It's going from, they tell you, chromium with an oxidation number of +6 to chromium with an oxidation number of +3. What's happening to the chromium? If it goes from chromium 6 to chromium 3, which means it is right. Because if something is oxidized, something else has to be reduced. So in this reaction, the chromium is being reduced and the alcohol is being oxidized. Does that make sense? Because in reduction, you have both processes. We only talked really about the organic ones going on, but the opposite process is there. And so when you have a transition metal, it'll change color to indicate, to give you a visual cue that the reaction has taken place. And that's why I said in a couple weeks we're going to see. We're going to do a lab on chemical test once we went through all of them, so you can see them all in action. Yes?
The condition's different for reduction.
We'll look at the ones for reduction in a little bit. This is not reduction. These are oxidation reactions still. We haven't done reduction yet. So we're good? Okay. So this is a very old school meme, but I love it so much. It's got some chromium. It's another version of a chromium oxide, but you get the idea. Chromium with a lot of oxygen. This does the same thing as Cr2O7. It says, hey, aldehyde, you want to be a carboxylic acid? The aldehyde's like, you bet, with a smiley face. And then the ketone says, and then the reaction happens, right? And then the ketone says, me next. And then, not you. Not happening. Forever ketone. Forever ketone. Forever love. Ketones stay ketones. Ketones stay ketones. They cannot be oxidized anymore. So it's just to help you get that point home. Forever ketone. Or reaction. Ketones cannot be oxidized. Got it? That's actually one of the things I think I want to do for next year. I want to start putting more memes in. That takes its own amount of time. I used to send them out on Remind, but this year we lost the ability to. Got to put them more into presentations. All right, here we go. How many of the following compounds, so what paper is this? 1, 2, 3? 1. What question number is this? Fun fact. Where do you think the organic questions are on a Cambridge paper 1? 25 through 40. If you know what you want to go for, organic is around 25 to 40. It's a good portion. It is like approaching 40%. Could be 40% up to. You can start a little bit earlier too. So, but definitely you can prepare 25 to 40 to be questions on organic. Here we go. How many of the compounds produce a carboxylic acid? Does the first one give you a carboxylic acid? Do aldehydes become carboxylic acids? Yes, they do. Always. Do ketones? This is a ketone, right? If you write it out, you'll see this is a ketone. Is that going to become carboxylic acid? No. Cheers. Bring it down. That's how you pick sad ketone. Next. What about that primary alcohol? Is that looking like it could be a carboxylic acid? Sure, because primary alcohols become aldehydes and aldehydes become carboxylic acids, right? So check mark. And then what about that one right there? CH3, CHOH, CH3.
Nope.
What's that?
Tertiary alcohol.
That's the secondary alcohol. And it becomes a ketone, and then it's forced to stay a
Forever
ketone, forever ketone. So that's a no. So the answer here is,
I said
you were right then. The answer here is 2. Good with that? How quick could this be to answer if you know your information?
It would take me hours.
Hours?
The entire time.
How much time do you get per question?
Like a minute.
Carboxylic acid is not.
75 minutes divided by 40 questions. That's your average time per question on paper 1.
It's more like a minute and a half.
All right, next one. You got some good old carbohydrates, monosaccharide, sorbitol. This is the artificial sweetener. You can buy it. What? You can buy it. You can eat it. If you go to the grocery store and you purchase like those diet chocolates, they oftentimes have sorbitol or some other sugar alcohol because based on the position of the OH just flipping its position on the chiral center, your body can or cannot process it. So your body gets no calories from this. Actually, it goes through you. Now the bad thing is it goes through you. Is the like a Metamucil or a like something that will go through you, but you can't absorb it. Literally just because of the positions of the OH. That's crazy, right? Biochemistry is crazy because of the chirality. However, this question doesn't ask us about chirality, although it could. This is suitable for diabetics, meaning it doesn't raise their blood sugar. What functional groups can be produced when this molecule is oxidized under any suitable condition? Can you get an aldehyde?
Yes.
Yeah. Is that a primary alcohol?
You get all these.
Can you get a carboxylic acid?
Yes.
Sure. Can you get a ketone?
Yes.
Primary alcohol. So the answer is all the above. Primary alcohol goes to aldehyde, which then can go to carboxylic acid.
Primary is aldehyde, secondary is carboxylic.
No,
Secondary goes to ketone.
Secondary is ketone. Primary is aldehyde, and which tertiary stays alcohol.
That's it.
What about carboxylic acid?
Primary turns into aldehyde, which turns
Which can
into
turn into carboxylic acid.
So aldehyde becomes carboxylic acid.
Yeah.
So one.
All right, next one.
So one.
What question number is that?
That's number 38.
38, still organic.
We're almost done with the test.
Which compound when heated, under reflux, with excess hot K2CR2, K2CR207, you have a product with a chiral center. Can you be asked about chirality still? Sure you can. How exciting. Take a look at number 1. What does number 1 give you? Is that a primary, secondary, or tertiary alcohol?
Primary.
So it's definitely going to be a carboxylic acid. Do you agree?
Yes.
Is this chiral?
No.
Is this carbon chiral?
Yes, yes it is.
Yes, it is.
Yeah.
1, 2, 3, 4. 4 different groups. That's chiral. So far, so good? Second one. Carboxylic acid you can't oxidize anymore. It's already the most oxidized form. But here, can this be oxidized? What type of alcohol is that? It's on the end.
Primary.
It's primary, so it turns this to a carboxylic acid. Is this carbon chiral?
That's the one on the right at the bottom.
COOH
Same thing.
and CO2H are the
Same.
same thing. Do you agree?
Yes.
So because these are the same, it's not chiral.
So we can cross off
So it's either
A,
D,
or D.
You can cross out everything.
yes,
Oh, yeah.
D.
Once you find out, that's how it used to be, the old test, before 2022. Just pick D if you can prove 2 is wrong. If you can prove 2 is wrong, it has to be D.
But why is D?
We can go over that. So, you've got CH3, C, ketone, C, ester, right? We're going to esters next class. Esters next class. What's CHOH? What type of alcohol is that?
CHOH is the primary.
Secondary.
Oh.
So, if it's CHOH, CH3, what happens to these 2 hydrogens? They would get taken away. And you would put a double bond, right?
Yeah.
And are these the same as each other, these 2 sides?
Yes.
So is this chiral?
No.
If any 2 sides are the same, it is not chiral.
From the same fact.
Yes?
Same fact.
So you didn't have to prove it, but we could. All right. Our speed is pretty good so far. All those cameras. All right. So we did oxidation. Now we're ready to talk about the inverse process, which is called reduction. So there's, in my opinion, good news here. What is reduction again? In the organic biology sense? Add H or take away O. So you're reducing agents, meaning the things that you use to reduce your organic molecule are either NADH4 or LiALH4. What's in common?
More hydrogens.
They got a lot of, so lots of hydrogens. Before this, you've never even seen these compounds, I don't think, before. Lots of hydrogens. So lots of hydrogens means that you are going to be doing a reduction. Lots of oxygens means you're going to be doing an oxidation. And so what you'll notice is this is the inverse process. A carboxylic acid will turn back into an aldehyde, but automatically that turns back into a primary alcohol. So you got COOH going to CH2OH. Reducing. Add hydrogen, take away oxygen. Here you've got another example. It's a benzene with a carboxylic acid. Does the same thing. Something important to note, that it's going to come up, I think, in a future slide, but it's important to note that LiALH4 and you may want to write it down, is stronger than NADH4. So if you want something that will reduce
Best.
any group, you use LiALH4. If you want a softer reducing agent that's not as harsh, you use NADH4, but it doesn't reduce everything. So it depends. LiALH4 is very powerful, which also means it's more dangerous than NADH4. And so we'll go over some more conditions on the next slide.
Well, you could drink
Actually,
it
when I was reading through earlier, they were mentioning that it's so violently reactive in water. The specific condition I'm going to give you in a moment is dry ether. You have to use ether as the solvent and not water.
Theoretically, you can drink it
cannot
once. You can drink it once in your life.
But that's it.
Yeah.
How many calories is that?
I don't think it's any calories.
I don't think
For the reason I told you before.
I don't think someone has 4 billion calories.
All right. Important. Write this down. First of all, NADH4 only reduces carbonyls. Do you remember what those were? Aldehydes and ketones.
Oh, okay, so carboxylic acids can be produced by LA.
Exactly. So LiALH4 will reduce carbonyls. It is stronger, but it will also reduce carboxylic acids, and that's what you have to be careful with. So this reduces carbonyls and carboxylic acid. So the whole thing, everything that can get reduced does get reduced, except for alkenes. Alkenes cannot be reduced by either of these. Alkenes, you need H2 and nickel to reduce them. Condition. I did want to bring up the condition because I believe I did not write it anywhere. It's dry ether. Dry ether. So you may want to fill that in. And H plus. H plus for acid. You'll notice in the examples here that it mentions the H plus already. It mentioned it as H3O plus, but you could write H3O plus and H plus are the same. But I mentioned that in other possibilities. On the next slide, when you're ready, there's going to say mechanism. This mechanism does not need to be memorized. It is for your knowledge only, like just if you like mechanisms, how does this happen? Some people want to know, how does this happen? So how does it work? This is actually the molecule BH4 minus, and 2 electrons from here go right there, and 2 electrons from here go there. And so you have a hydrogen adding in, and you've got oxygen with a minus charge. Then that grabs the H plus, and the Na plus is the spectator here, and you get your final product. And so this is the reaction. However, you do not have to memorize. Unless you want it to know for your own benefit, you do not need to memorize this mechanism. I just included it for you, in case. Now, what do we need to know how to do? This. I think this is a question 36.
Okay, so that's reduction.
Diagram shows Z. NADH4 tells me what am I doing? What does excess mean?
Excess means it's enough. More than needed.
Meaning if it could happen more than once or you can reduce more than 2 groups, you have the ability to do that. So it would happen. So your question is to identify each of your functional groups and see if they can be reduced. So can you reduce aldehyde with NADH4?
Yes.
And you would do that by doing what? Adding and breaking up this double bond, right? Can you do the same thing with ketones, with NADH4?
No.
Yes, because that's a carbonyl.
No, the
It's
carbon
the other one, the double bond.
Why is it
The
that-
C.
Can you do that with alkene?
Yes.
Does NADH4 react with alkene? Is NADH4 what we use for alkenes?
No.
No, we use H2 and nickel, right?
Yeah.
So it's not. So not this. So what's the answer? Thanks. Because you have access, so it can happen more than once. Carbonyls get reduced, meaning you add the hydrogen. Carboxylic acids would not, but you don't have one here. All right. I realized when I was reading earlier today that you skipped this. I have been moving stuff around, and we are not at nitriles yet. That's another day. So skip this question. Just put an X. Now, this one, 8C, still should be included. Name and give the formula of the reducing agent used to convert carboxylic acid. And I don't know if I stated the name here, but I'll tell you what it is. It's LiAlH4. The name of that is called lithium aluminum hydride. Lithium aluminum, if it shows up.
Hydride.
I've never seen them ask you for the full name on a paper two, but it's not a type of scope on a paper one for them to write it out what the full name is. Now, an interesting thing about this, the oxidation number of hydrogen here is not positive.
It is zero.
Fun fact. In oxidation numbers, we learned that oxygen was almost always -2 and hydrogen was almost always +1. When is the only time hydrogen is not +1?
Reduction.
When it's combined with a metal. If lithium has a +1 charge, just go through this in your head, and aluminum has a +3, what charge does hydrogen have to have for the whole thing to be equal to 0?
1, -1.
Each one has to be -1, right? Because -1 times 4 is -4. This is one of the only times hydrogen has an oxidation number of -1. Just a fun fact for you. So, if lithium aluminum hydride is reducing, what do you think is happening to it? It is being,
Adding hydrogen.
it would add hydrogen, so it's reducing. So what happens to it as a result? Like, if the reaction occurs, what would happen to lithium aluminum hydride?
It would have a negative charge.
It would be oxidized, right? So if this reduces, this is oxidized. Which really means you're going to be turning at least one of your hydrogens from a -1 charge into a +1 charge, the way that it normally is. You're flipping the oxidation state of hydrogen. If you look at the mechanism, back here, it's a little bit in there because if one of these hydrogens joins with OH, what oxidation number does this hydrogen have? And what was it in here? So it changes from -1 to +1, right? It's oxidized. Just throwing that out there.
Also, hydrogens are oxidized.
Right. They do the reducing,
Okay.
so that's why it's called a reducing agent. It's not different from what we learned earlier this year. We just don't really look at the numbers so much anymore. All right. Conditions. What was the thing I said you needed to include? Dry, ether, and H+. Okay, so I think this is the final thing, and then we have a question, and then I want to show you a Starburst before you get your study time. So I had mentioned in passing to write down the word distill. That alcohols that were primary would turn to aldehydes, and those aldehydes would turn into carboxylic acid. But this procedure outlines how to keep an aldehyde. An aldehyde. Meaning, how do we stop the aldehyde from becoming a carboxylic acid? And we're going to go in deep into the recesses of our memory. Let's say we have ethanol, right? CH3, CH2OH. And that turns into an aldehyde, same amount of carbons. That aldehyde would be ethanal, CH3, CHO. And then when that gets oxidized again, it gets turned into carboxylic acid. So, alcohols have a specific functional group you need to be aware of. That specific functional group is that you need to be aware of is called the alcohol. And so let's go back to the intermolecular forces. Alcohol has what intermolecular force? Something stronger. Hydrogen bonding. And so what about aldehyde? What is the strongest intermolecular force for aldehyde? What? Permanent dipole. Or PV. And what about carboxylic acid? What do you think? Carboxylic acid. What is the strongest? Correct. Hydrogen bonding. So, go back to the deep recesses of your memory. Melting points and boiling points. How does intermolecular force affect them?
Stronger the bond, the stronger, the higher the bond.
So the higher the melting point, the higher the intermolecular force. Notice something here. Hydrogen bond, permanent dipole, hydrogen bond. Are any of these forces weaker than the other?
Permanent dipole.
Right. So here's the idea. If you pick a temperature that is greater, go ahead, is greater than the intermolecular force here, but weaker than the intermolecular force here, kind of like a Goldilocks temperature, you can distill out the aldehyde. So what does distill mean? What does distill mean?
Like neutralize.
You know what distilled water is? We use it for our labs. What does distill mean? It means oil out. So, the idea is that if you pick a temperature that's lower than that of the alcohol or the carboxylic acid, but higher than that of the aldehyde, you can boil out the aldehyde. And so that's what they're saying here. To keep the product as an aldehyde, you would boil it out by picking a temperature in between. So it has to be boiled out as soon as it forms. Well, how can you do that? You need a device to collect the gas out. And so I don't know if I have this set up here, but I did have one in another lesson. You would basically have your reaction mixture, and then you would have some device that collects the gas out. So you would basically distill out the aldehyde into a separate container. I mean, you could if you want to distill yourself some water, right? You could take tap water and distill it and then get rid of all the ions from the water. Totally something that can be done. All right. So this next slide is from special procedure to keep the oxidation of any aldehyde. This is just from what I found on a revision guide. But I have seen questions where they ask you about this process And I would specifically point out the difference in the intermolecular forces, the difference in the boiling point, and that because an aldehyde has a lower boiling point, it would distill out first. So you could collect your aldehyde as soon as it's being made. That's the idea. They say to slowly drip the solution and then keep the temperature of the flask in between the two boiling points. That's exactly what I was bringing up. So the idea is that if you've got your boiling point of your
We have,
alcohol, not on this specific thing, your boiling point of your carboxylic acid and your boiling point of your aldehyde would be the least. So you have to pick a boiling point that's somewhere in between here. You have to pick it to be higher than your aldehyde but less than your alcohol or your carboxylic acid. That's the idea. So boiling point of the aldehyde, lowest, then alcohol, then carboxylic acid. This is a very, very specific procedure that could be worth a couple marks on a paper too if they decide to ask about it. And it can also show up as just the word distill in a question. So if they say distill, it means the aldehyde stays in aldehyde at that point. So let's take a look. This doesn't actually really have that process. It just tells you you have a mild oxidizing agent, and then you have NADH4. So, if you have an oxidizer, will it oxidize an aldehyde? They didn't mention the word distill. Does it happen? So what does this turn into? So right now you have COOH at the top, and what else? That's not aldehyde. Ketone, right? All right. Now you've got NADH4. What happens now?
It reduces.
You're reducing the NADH4
That's it.
to no. Does NADH4 reduce carboxylic acid? What does it reduce? So it would reduce your aldehyde corridor to what? This, right? What answer is that? E.
LCH.
It's,
Which answer is it?
I'm with you.
LCH3.
It makes sense.
What about the double bond? Is there anything with the double bond?
Okay, whoops, I
The
didn't,
answer is
I didn't know.
Alright, let's check again.
Carbon.
Aldehyde gets changed to 2A, carboxylic acid. NADH4 only reduces carbonyls. So, it's a secondary alcohol. That's the answer. Alright, so that's the new content for the day. But before you get a little bit of time to review for your third mini assessment, I wanted to do a couple of things with you. The first one is I wanted to teach you a way to organize your thoughts. It's called a starburst. When we're reviewing, we'll make more of these, but I wanted to start with one that we are a little bit familiar with, which is reactions of alkenes. So if you already wrote over this spot, starburst for alkenes, you'll notice on the very, very back of the handout today, I've left it completely blank. So if you want to use the whole page for this, you can. Or you can use the spot that's in slide 3 for the starburst of alkene. We're going to start with an example alkene, and then we're going to do all the things that alkene can do. So I'm going to give you an example alkene in the middle, CH3, CH, CH, CH3. Put it in the middle, and we're going to start shooting arrows out of it. So all the things you can do. And where did we begin? We started with, but that's not specific to alkenes, is it? It's specific to alkane. So let's start with all the things we know alkenes can do. But let's hold that because we can add it in at the end. First, let's start with the addition reactions. What can we add to an alkene? Do you remember? We can add H2. And what would be the condition? Nickel? Nickel? Or you could say platinum, one of the two, right? You don't have to put both. And what's that? So that would be CH3, and you should write this down. CH2, CH2, CH3. That's one thing. This turns an alkene into an alkane. What else can we add? Go ahead, Dan. Steam. So we can do plus steam, which oftentimes you'll just see us write it as H2O. Yes. What are the conditions for this one? H3PO4. And anything else? Just heat. I mean, it's heat because it's steam, right? So I think that captures it already. Saying it's H2O gas. It's hot. Now, what's the product here? Doesn't matter where.
In the middle, closer to
It
middle.
doesn't matter. It's maybe.
Because I intentionally chose something symmetrical. But would Markovnikov's rule apply if it wasn't symmetrical?
Yeah.
It would. So you can make these as easy or difficult as you want to. And this gets us to an alcohol. What type of alcohol is this?
A ketone? No,
It can become a ketone.
a secondary.
So you should write that. Because you're going to get multiple step questions. Once you have a secondary alcohol, what could you do with that? That we just learned right now.
And two ketone.
You could then oxidize it and turn it into a ketone. All right, what else can we do?
We can do
We did H2, we did steam. There's more. We can add a halogen, right? Pick a halogen, any halogen. Chlorine, okay, Cl2. Bubble that in carefully because that's warfare. Chlorine. No special conditions for that one, right? Room temperature's fine. So what happens? CH3, HCl, CHCl, CH3. What else? We could add it to itself. What about HCl? What about HCl? We didn't do that addition reaction yet. HX. What would happen with that one? What would you
One
get?
hydrogen, one carbon would get a hydrogen, one would get a.
Perfect. Now what? I heard a lot of good answers. Somebody said, what about the KMNO4 cold versus hot? Right? So KMNO4? KMNO4 H plus cold. What will we get from that?
We break the double bond and add hydrogen to CH3.
Is it nickel or?
Or platinum?
So if you
No,
see,
it's and. Nickel or platinum. And heat. The slash means both.
if you just have KMNO4 cold, wouldn't it just be what's it called? Butane?
Gotta add oxygens, right?
Oh, and so,
CH3, CHOH,
oh, okay.
CHOH, CH3. Parentheses around the OH just to be sure.
Also, you add oxygen and hydrogen.
OH to both sides, right? The diol. What else? There's more alkenes can do.
Hot KMNO4.
Now we got hot KMNO4, right? Split it in half. You get CH3,
CH, double bond.
C, double bond OOH. And technically it's the same thing on both sides. So you could just put a 2 in front for this example.
Yeah. Nucleophile substitution.
Addition polymerization, right? So we would just say with itself, right? Umpteen amount of times. With itself. Remember that with addition polymerization, you should prepare yourself by writing it a specific way. Remember? So that you can break the double bond, go like this, put the N, and then the CH3. Okay, how much more? You remember this? Addition polymerization. That was a thing we did,
Yeah, that's what would be N.
right? With a little N. Anything else? Some people mentioned, I heard free radical substitution. And although free radical substitution isn't diagnostic of an alkene, could it not be used in an alkene since there's an alkane?
Yes.
So you could, if you felt like it, add UV light and pick a halogen, except for fluorine. Pick a-
I remember all of these. Yeah, remember.
This is what we went over, isn't it?
Yes.
And pick a hydrogen to swap out, right? You get multiple different products, you just pick one. I'm gonna do CH2Br and then CH double bond CH3. This unaffects the alkene, right? No effect on the alkene. What else can alkenes do? There's one more I'm thinking of that you might forget. You forgot it on the first mini assessment. What could it be? It's always there. It's the only one you would know in pre-ACE, burning. The only one you would know, which is combustion plus O2 and heat, and you would make the product CO2 and H2O. You just have to balance it, right? This is an example of a starburst. You could do a starburst for every functional group. We're done with the whole unit. We have only completed alkenes, right? We are in the process of completing alcohols. We should be done with alcohols next class, actually. Alkenes and alcohols are the heftiest. And halogen alkanes probably, because those are the ones we have the nucleophilic substitutions for. So this is just to give you an idea of what you can do to help make a mental map. You can start with any starting compound and you can react with all these different things. And it just helps you to figure out what you need to do. All right, before you take the quiz and get a little bit of time, let's do some practice reactions to prepare for that mini assessment. So you'll notice in the back I wrote practice questions. This was to give you some time to practice before taking the mini assessment. I want you to try these yourself. Basically just a little pre-test. Here we go. Write it on your paper, write your answer. To get better, you constantly have to quiz yourself, test yourself. As many practice questions as possible is the way we need to go. Yes, this product. Major organic products.
It's great spots. It's supposed to be more electronic. Right?
20 more seconds to check to see if you got it. First of all, what type of reaction question do we have?
Nucleophilic substitute.
Yes.
Okay.
And so the iodine gets out, and you've got to remember it's NH2 plus HI.
Right, because it
Because
uses the bond to get
nitrogen
to an
only makes 3 bonds. It has to be NH2.
What's the name of this again?
Nucleophilic substitution.
No.
Iodine gets out. Oh, an amine. You make an amine. This is a amine. Right? All right.
No, you make.
Try another one. Try to make an amine or smelly stuff. Smells like fish. All right. Let's try another one.
It's like what something. Holy.
Ready? Yes. Go ahead. So see if you can do it. I'm giving you a little bit of time to think through it first. This is to test yourself. Yes. That's our final unit, yes? Just to memorize organic chemistry reaction. Organic chemistry? Yes. Almost. You're missing one line. At the top. What would you do? If you want me to check before I put it up on the board, I'll check for you. You need to make sure there's a double bond. Because you have them as alcohol.
No, it wasn't.
All right. Correct. Oh, correct. Anybody else ready for me to check? This is correct.
My brain is just so big.
All right, 30 more seconds. I'm going to put this up and do the next one.
Yeah, that's not wrong.
I don't know.
You see. But there's a ring. Where's the ring?
Garden ring.
All right, I'm going over the answer. It's this. You should have a ketone on one side and a carboxylic acid on the other.
Oh, right, the brain is two things.
Or you could have written it as one line, 1, 2, 3, 4, 5, 6, and then had your carboxylic acid on one side and your ketone on the other. And then it would be one more, 7 for the ketone at the end here. Right? Because it would open here. 7. All right. Next.
Yeah,
That's an oxygen.
if it's full,
It's
also
also
the
able
able before.
It's square.
Miss,
Yeah,
I got a question.
go ahead.
One starts into O, the other one CH.
Yeah. This is an aldehyde. Aldehyde, don't say aldehyde, you're trying to carboxylic acid.
Oh, the aldehyde becomes a carboxylic
And the
acid.
ketone basic. Basic.
Oh, okay, that makes much more sense.
Yes, ready?
says to keep it there.
Oye, mijo.
Concentrate. You had a brain, maybe you can concentrate.
Beautiful.
I haven't done the one for last class.
All right, we'll do one more. One more. No. An OH and an OH here. Pulse. And a OH and an OH here. Two double alcohol. Because it's excess. So it happens again and again and again.
Just the ends of the.
Double one.
We're gonna do one more. One more.
No.
Yeah.
I'm gonna delete this.
I'm feeling ready for the other.
Delete.
For the ad.
What?
Okay, that way.
Okay. Okay. Okay.
I agree.
Well, buddy, I got the.
No, you don't.
No, yeah, you're right. I mean, it's symmetrical.
All right.
Now, what do you have?
If he goes there, then everything else goes. Yes. Yes.
Yes, that's how it always is.
Go.
Let's check them out.
Just that makes no sense. It is a sun. I think yes. You know what? It does absolutely nothing. I don't know how to do this one. This one I don't know how to do.
This is the one I forgot.
Yes,
It
this
was
is
on
one
the
I-
last mini assessment, right?
Yeah, that's why I got this one.
Yeah.
I cried when I saw it.
What'd you get?
Well, one last point.
I got a 50. Less than you.
I got like a 2. I think I got 2.
What do you got? What do you got?
Yes, I got. Okay, you know what? Let's just assume that it goes
Sorry,
It's double bonds on every single one.
Nope. If it was aqueous, it would be correct, but it's not aqueous. I mean, if we'll do this, the next one then.
Ain't no way to be.
There, like that.
It looks familiar.
Yeah.
All right, so this is for elimination. You make an alkene with NaOH,
Oh yeah.
ethanol. So you just have to rewrite all this. And it doesn't matter, it's symmetrical. You can do your double bond there or your double bond on the other side. That's the first one. What about AQ? What's the difference? Come on. If it's AQ instead, what's the difference? It's not an elimination, it's a substitution. So Br gets out and OH gets,
Wait, if you see ethanol,
it's an elimination.
okay.
And if it's AQ, it's a substitution. And so this would then be,
Oh, that's what I thought it was. Okay.
so that's the big difference between those two. Same molecule, if it's ethanol in NaOH, it's an elimination. If it's aqueous in NaOH, it's a substitution. All right, so what we're gonna do is you have a little bit of time till 2:05. You can study on your own or study with each other, study your flashcards, do other practice questions. Say this was lesson 4, 5, and this was lesson 2. Everything with the mechanism. mechanisms flashcards. So what?
What did you say?
Unit 6, lesson 4.
Oh, it's an percentage of the group.
As a mock, as the same as an examiner, you keep it.
Oh.
Yeah, the average of the highest 6. The average of your highest 6 assessments. You can fumble only a paper. 1/3 of them. You have a bad day for you. Can't fumble more than 30. Is it only 2?
But.
All right, use your time. Study your flashcards.